This is the first of 3 lectures that will deal with probability and simulation. Our goal is to start out with relatively basic concepts of probability and then build to more complicated business situations. In all cases, what we're trying to do is to, in essence, predict the future. Now, predict the future has always been risky business. Prophets in Old Testament Israel were stoned to death, I suppose, if they were quote-unquote false prophets. And predicting the business future today is no simple matter. What we want to do, however, is to, in this lecture, build the foundation to begin to think about simulating future events, to try to get our hands around what might happen and what the likelihood of differing events occurring is. So in this lecture, I'll provide an overview of the lecture. And first, we're going to talk about the goal of probability. We'll talk a little bit about on predicting the future. We'll talk about a model for refining intuition. We'll discuss experimental probability. And finally, we'll talk about different ways of deriving probability estimates. And in subsequent lectures, we'll build probabilities about more complicated events, because remember, business situations, as well as in personal life, complexity tends to be the norm. And the extent to which we can build a model which handles that complexity, that subtlety, we have developed a more and more adequate model for dealing with data. Now, this is very different than statistics, as I've mentioned, where with statistics you start with a data set, and then you observe what's happened, and then you talk about, well, how my world works. The average age for the teaching company employees is X, or the average salary of those attending Dodger Stadium is Y. With probability, the goal of probability is to understand what is likely to happen in future situations within systems you know something about. So it's not as if I'm trying to define this world through statistical analysis, like I'm trying to estimate a population, a parameter with a sample statistic, as we were talking about in the last lecture. What I'm trying to do now is start with something that I know something about and predict what is likely to happen in the future given some systems that I know. Now here I have a marker. It's a red marker that I've been using periodically to work with this whiteboard. Now I can toss this marker, and I'm about ready to give it a flip, and I just barely caught it. There was some probability assessment as to whether or not I would catch it. But in fact that I did, and I suppose that I did, relates to the fact that I have built a model in my mind as to the flight trajectory of that pen. I didn't know exactly where it was going to go when I tossed it. I gave it a certain force, and it has a certain mass and a certain acceleration, which deals with, or deceleration, given to the force of gravity. I didn't know exactly its flight path. But in my mind, having played baseball in high school and having shagged hundreds and hundreds and hundreds of fly balls, and having played catch, day after day after day, I built up an experiential model in my mind as to what the likely flight of that pen was going to be. So I had, in essence, built up a probabilistic model in my mind, which was not based on force equals mass times acceleration or some Newtonian model, but actually was based on some type of experiential model which dealt with what I thought the flight pattern of the pen was likely to be. Now, had I missed it, I would have picked it up and tried it again. I would have been sure to have caught it at least one time to demonstrate the fact that I've not lost all facility in being able to judge the flight path of the pen. So I was guaranteed to win. I was going to keep tossing this until I eventually caught it. So this is an example of predicting the future. In essence, if I have a good model, in this case, my mind had developed a pretty good model, although I had to make adjustment for these lights in my eyes, and I would have done that had I missed it. I came up with a pretty good way of predicting the future path of this pen. When we build probabilistic models in business, we try to do some very similar things. We try to get assessments as far as likelihoods of things like competitors entering our market, of likelihoods of various revenue patterns or cost patterns, and we try to build a model which enables us to forecast the future. Oftentimes we don't forecast the future with point precision. We get certain probabilistic ranges as to the likelihood of our cash flows or the likelihood of our revenue stream. And in subsequent lectures, I'll illustrate to you some sample simulation models which try to develop likely revenue streams or cash flow streams. But essentially, probability is about this. It's about trying to give some sense of what is likely to happen in uncertain future situations within systems we know something about. Now, if we don't know anything about the system, there's things we can try to do, but we're more in chaos theory than probabilistic modeling. So here, my focus is on trying to talk about probability. Now, in order to talk about probability, we have to kind of start at the start, and that is build up our knowledge of it to be sure we have, again, a common definitional language that we can proceed from. That's what I'm going to do in this lecture. In the next lecture, I'm going to talk about combining events that deal with more complexity. And then in the fifth lecture, I'll give a lecture on simulation to illustrate what it is like to build a simulation model that tries to deal with a business situation which is relatively subtle. Let's once again re-emphasize the difference between probability and statistics. I've mentioned this point before, but I think it's well worth stressing again. So let me come over to the whiteboard and remind you that when we're in the domain of statistics, we make some measurements. We sample the teaching company's population as far as average age or whatever, demographics, and we get a measurement as to what happened. And then, statistically, we try to make some statement about how our world, or the world in this case, works. We try to make some statement that says, like, the average salary of the teaching company customer is blah, blah, blah. Okay? That's the statistical process, moving from what happened from a data set that we work with and deal with to how our world works. With probability, we start with how the world works. Now, when I tossed this pen, I had in my mind a model about how the flight path of that pen was going to be. And consequently, I had a model in my mind that I had built up experientially. And oftentimes, we build up experiential models. This is why sometimes entrepreneurs seem to the outside observer to be taking very, very big risks, whereas in their minds, they don't feel like it's that big a risk at all because experientially they've been here and thought about this and have a great deal of experiential data in which they're making their probabilistic judgments about whether to spend this money on marketing or whether to enter this new market or tackle this venture. So oftentimes what appears to be risky to them, to us, to them seems to be almost like a sure bet given their experiential view of how the world works and the adequacy of the model that they have built to describe how the world works. Because with probability and with simulation and other model building type of techniques, what we're trying to do is to start off with a point of view as to how the world works and then to move to what will happen. Notice these are, in a sense, inverse of each other, and the processes are moving in opposite directions. Their starting point is the ending point for each other. So, if I start out here with some comparable data, like we were talking about last time, for stock prices, and I'm trying to price an initial public offering, and I have a data set and observing what happened, that this average company in this industry, let's say it's a high-growth software company, and high-growth software companies tend to be priced on the basis of revenue as opposed to earnings. They may not have any earnings. So I may price these software companies, comparable software companies, at 2 to 3 times earnings. The way some of these stocks are priced these days, that's a modest valuation. But that's an observation, and then I'm trying to statistically infer about how the world works and therefore be able to make a judgment as far as how I should price my initial public offering. So today we're going to be focusing now on this probabilistic dimension, where we'll start off with a view of how the world works, and we're going to try to infer what's going to happen. Let me talk about a model for refining intuition. In fact, most of business judgment could be viewed as building upon this model. Let me spend a few minutes describing the model to you. It starts with raw intuition. I have to make a decision. I really don't know exactly what I should do, but I maybe have some native raw intuition. And as I've said to you before, some entrepreneurs have very highly refined intuition given decades of experience, or maybe just some natural sense of a market. Maybe they're going to create a market as opposed to have a lot of data about the market, and they have a sense for where this market may be going. Now, I want to refine that intuition. I want to move to heighten my intuition, to make it more seasoned. There's 2 fundamental ways in which I can do this. I can get access to information. I can either download it or create it or build a data set that gives me information about this market. Maybe it's qualitative information. Maybe I go out and find out who all my competitors are. And these days, that's becoming much more complicated than it used to be. It used to be that, competitively speaking, we could identify 3 or 4 or 5 companies, and we say these are our competitors. Today, we have the phenomenon of digital convergence, and it seems like that who my competitors are is an ever-increasing array of companies that are impacting my market. And I have to think very long and hard about who my competitors are. Well, in any case, if I want to refine my intuition, I can get access to that information, be it soft, qualitative information, be it hard data, which deals with a statistical analysis, data which is subject to statistical analysis. Or I might also be able to gain access to expertise. Now, access to expertise can help me a great deal, too, in refining my intuition, because if I can talk to somebody who really is knowledgeable, someone who has been around the block, so we speak, about this problem, someone who's expert in this area, it can help me a great deal to refine my intuition, because this person, this expert, can add a great deal of value to my thinking. Now, if I have the data, notice that I also can refine my intuition by doing analytical modeling. And this is, of course, what we're focusing on here, that if I access the information, I can refine it by taking that data and building some type of model which enables me to see things in that data set which I might not have seen before. This is what we mean by analytical modeling, refining my business intuition. The ultimate goal is to take raw, native intuition and to move it to more heightened, refined awareness of my business situation, which theoretically and practically speaking will increase my effectiveness in decision making. Now, of course, there's a whole other dimension to it, and that is I might even know what to do. My decision might be correct, and then I still have to do it. I still have to implement it. I still have to get it done. And oftentimes there are people, maybe you know, and certainly that I know, that are marvelous in understanding what needs to be done, but seemingly impotent relative to being able to execute. And of course, so much of effective decision making and intuition building, and execution has to do with being able to implement effectively. Now, let's talk about probability more specifically. Let's talk about experimental probability. Now, there are many forms of probability. I'm going to cover others, but for right now, let's start with experimental probability. There are 4 dimensions to it that I want to be sure that you're clear about. The first is the random experiment. This is a procedure that produces an outcome that cannot be perfectly predicted in advance. And I'll give you illustrations of each of these as we go through the material. The sample space. The sample space is a list of all possible outcomes of my experiment. The outcome. This is actually the actual result that occurs when I run the experiment, when I run a random experiment. And the event. The event is any collection of outcomes that are specified in advance. And this sounds abstract at this point in time, so let me give you an illustration to try to put some flesh around these rather abstract ideas. But if we're thinking about experimental probability, think about these 4 dimensions: a random experiment, a sample space, an outcome, and an event. And you'll have a good sense as to what we mean by experimental probability. And oftentimes, in experimental probability, we're not just talking about scientific experiment, we're talking about business experiment, where we're trying to develop good assessments of probabilities for us to be able to build a more effective model for our business planning purposes or business decision purposes. Let's say, let me give you an illustration. Let's say that Compaq, a computer manufacturer, wants to study whether or not Hewlett-Packard, another computer hardware manufacturer, will match its price cuts in the server market, the computer server market, relating to classes of servers. So first of all, that is, and we're going to do a test. We're Compaq, and now we want to check whether or not HP, Hewlett-Packard, is going to match our price cuts. So that is the experiment. It's random in the sense that we don't know its outcome in advance. We don't know exactly how it's going to be. And we have to set up a procedure now that will enable us to see what's going to occur. It can't be predicted. We don't know exactly. It can't be perfectly predicted. Maybe if we have someone with heightened seasoned experience and intuition, they could do a good job. So if you look at the green board here, I have HP response. True condition here is a match. And I've got 3 classes of servers that I'm going to cut my prices. I'm Compaq. I'm going to cut prices on server 1, server 2, and server 3. Now, what is HP going to do? First of all, I'm going to run an experiment, a random experiment, to see what could occur. That is the random experiment relative to my price cuts. The sample space lists all possible outcomes of this experiment. In essence, this describes here the sample space. In other words, they could match me on all 3 servers, match my price cuts. They could do any of these combinations. For example, this one here would be they would match me on 1, but not 2, and they would match me on 3. Now, this is an illustration of the sample space. It's everything that could happen. It describes the entire universe of possibilities as to this random experiment. I've not put any probabilities, and I'm not postulating at this point that these are all equally likely. All I'm doing is listing the sample space to what could occur to illustrate what we mean by a sample space. Now, the outcome. I run the experiment. I actually announce I'm cutting my prices. And I observe experimentally now what Hewlett-Packard does. So let's say let's say that this is the outcome, that They match me on server 1 and server 2, but they don't match me on server 3. That is an outcome. That is the result that occurred when the random experiment was run. Okay? And finally, let me describe an event. An event is any collection of outcomes that I specify in advance. It's a subset of the sample space. Now let me give you an illustration. Let's say an event that I define to be Q is that event Q is that HP will match me on greater than or equal to 2/3 of my price cuts. In other words, they'll at least match me on 2. They might match me on 3. That's an event. Now it turns out that in this case that this would be favorable to Q because all 3 match. This would be favorable because server 1 and 2 matches. This one would be favorable, number 3, because number 1 and 3 match, and number 4 would also be favorable because 2 and 3 match. So these events, these outcomes would be favorable to Q. But the final 4 would not be favorable to Q because they don't match me on at least 2 of my price cuts. So, by the way, if all these outcomes were equally likely, which is, I'm not arguing, but it would be there would therefore be a 1/2 chance that Hewlett-Packard would match me on at least 2/3 of my price cuts because 4 of the outcomes are favorable to Q and 4 are not favorable to Q. But I'm not arguing that that's the probability that they'll match me because I don't know if these outcomes are all equally likely. I've not made that judgment yet. So the bottom line on experimental probability is this, that what you're trying to do is build up some basis for making probability judgments. And sometimes what we do is we run experiments. We run random experiments to see what the outcomes will be. So we might run customer surveys. And customer surveys may describe, I like this product that's featured with these automobile features versus these and I'm building up a probability assessment as to which feature is liked by my customer base. Now, as far as probability is concerned, let me talk a little bit more about it so you get a feel for what we're discussing, what's going on here. The probability of an event ranges between 0 and 1. Now, a probability that is at 0 essentially never happens. And I'll come back and explain that. And just when I say essentially never happens, I'll explain what that means. I also want to talk to you about how probability relates to the odds, because you may hear probability and the odds mentioned. I also want to talk about 4 ways of deriving probabilities. I've given you 1, but I want to discuss 4, including experimenting and calculating relative frequency, experience or subjective probabilities, counting possibilities, and mathematical calculation. These are 4 ways in which we tend to get probabilities. Now, why do we even want probabilities? Because when we have probabilities related to events, it will help us to talk about what's going to happen in future situations, and particularly as we start putting probabilities together, we may very well be able to deal with complex simulations. Let me go back to the fact that probability is between 0 and 1. If an event has probability 0, it means it essentially never happens. An example might be, I'm on a 550-yard par 5, which is, for those of you non-golfers, this is a very long hole. a probability of 0 would be essentially shooting a hole in one on a 575-yard hole. Even some of the longest hitters in golf, like John Daly, traditionally would not be able to hit the ball that far. Now, and I suppose that for most people it would be 0, and only in a very, very unusual event. For all practical purposes, you would. I don't think anyone has ever done it in the history of mankind. I suppose one could argue that if you had a great gigantic wind, a tornado, pick up the ball and drop it in the cup, it might occur, but essentially it's 0. It's not going to happen. Now, if you have a probability at 1, it means that it essentially always happens. To stay with the golf metaphor, for example, if I am a professional golfer and my ball is a 1/4 inch away from the cup, the chances of me missing that putt, which is sitting on the lip of the cup, don't exist hardly. You know, I suppose it could very rarely happen. I could get a heart attack, or I could, you know, hit the ground, you know, in some very unfortunate way. But essentially, a probability of 1 means that the event essentially will always happen. Now, most of us don't deal very often with events that have probability 0 or probability 1. Philosophically, we might argue that the probability of the sun rising in the morning is 1. We may not see it, but the fact that it rises. And other philosophers might say, no, that's not the case. That's just our subjective experience. We may be on a very lucky streak of sunrises occurring every morning. I mean, so here we get into epistemology and theories of knowledge and theories of metaphysics of reality. But essentially, probabilities do range between 0 and 1. However, I want to mention to you the following. In the long run, almost any event can happen. For example, if a few years ago we would have talked in terms of the demise of the Soviet Union, someone would say they had a very low probability of occurring. And yet, you know, the Berlin Wall's down, and events happen in the long run. And similarly, sometimes you see a grand company, a great company that's functioning well, that's well-oiled, that's everything's working for this company. And we think, what's the probability of it collapsing? And it's very, very low. In fact, in the long run, funny things happen. That the markets we deal with are quite dynamic, and in fact, it can occur that in the long run, most events can occur. So we have to be very careful sometimes about the time horizon in which we're estimating probabilities. Probability of 1/2 would mean, of course, that it is about to occur half of the time. And if we have a fair coin, and I say, what's the probability of flipping a head? Of course, that would be, for one toss, a probability of 0.5. Although I once had a physics professor that demonstrated how to flip 20 heads in a row in front of the class. In fact, it wasn't really flipping. It looked like it was flipping. And there's all types of things that we can do to play with probabilities. Now, let me talk about probability versus the odds. The probability that an event will happen is related to the odds at which that event will take place. So let's go to the horse races just for a minute. And let's say that a horse called Stewball, or whatever, has 9-to-1 odds. Okay? 9-to-1 odds on the horse. That means its probability is 1/10. Okay? So if you have odds of, p/1 odds, the probability associated with that is 1/p+1. In other words, if I have 1-to-1 odds, that means if you bet $2, you'll get $2 back. Of course, you get your $2 back plus the 2 that you win. 1-to-1 odds would be 1/2. the probability is considered an even bet, 1-to-1 odds. 9-to-1 odds means the probability is 1/10. So in general, if I am given p-to-1 odds on an event, it means the chances of that event occurring relate to 1 over p plus 1. Golfing events, the same thing. Whatever events we put odds on. If someone says, I'll give 3-to-1 odds that a competitor will come into your market space, direct competitor in this geographic area, that relates to a 1/4 probability, 3-to-1 odds. Now, let me talk to you about deriving probability, about how do we get probability estimates. I've already alluded to the fact that sometimes we experiment and get relative frequency, but let me illustrate this in some way. Let's say that I'm producing a product. Let's say that I am producing since I'm on golf today, let's talk about a golf club. And I'm producing a new, quote-unquote, super bubble golf club. They have all the, the way golf clubs are marketed today. Almost a new one comes out every week. And if I talk, and I put through 2,000 clubs, and I find 3 of them defective, okay? That means I have a defect rate of about 3 in 2,000, which relates to about less than 1%, 0.005. What this means is that what I'm doing is I am counting my number of times the events happened and I'm dividing it by the number of trials. So here's a production control issue. I run the experiment 2,000 times. I put 2,000 golf clubs through the production process. I get 3 defects. I talk in terms of the number of times the event happens. In this case, an event is a failure, a product defect. That gives me a relative frequency or probability of a defect which relates to 0.00115. This is the first way in which I might get a probability. I may actually run the random experiment a large number of times and see what occurs. Or, for example, I want to find my response rate. I want to find my response rate to going out to a certain customer mailing list. So I go out to 2,000 customers and I find three respond to my ad. And this is my response rate or probability of getting a response. Experimentally, I have gone through the process of trying to develop a probability. Now, this in itself may be not that useful to me. But what I can do with it is that I can use it a part of my thinking and planning to build something which enables me to model cash flows, or model to think in terms of what does it mean to me to be able to have this type of response rate. Now, secondly, we have experience or subjective probability. What this means is the following. And let me give you an illustration of subjective probability. This, again, is relative frequency. I'll take this one away and deal with subjective probability. Now, subjective probability assessments, sometimes we have to get them because we don't have any way of running the experiment necessarily. Or sometimes we feel that history will not be a good indicator of the future. For example, I've done work for a movie studio, in which case we were trying to develop some probability assessment that they would have what we call a breakout film. A breakout film means that at the domestic theatrical box office, it does $100 million or more. That's traditionally what Hollywood calls a breakout film. So we might look at a film studio's previous movies, look how many movies it did. Let's say it did 100 films over the last 5 years, and 10 of them broke out. That would give me a relative frequency probability of 10%. The probability of a breakout is 10%, which assumes what? This assumes that the future will reflect the past. And if in fact now I brought in a new studio director, or I have some new in with a talent agency, if that's meaningful, the future may deviate. It may depart from the past. So what I may do is go to the CFO of the company and say, or whomever I'm working with, in the past you have had 10% breakout ratio. The probability of you getting a breakout is 10%. And by the way, Hollywood lives for the breakout. If it doesn't, the film studio does not get this breakout, the economics tend not to work very well. It doesn't typically, for most studios, work to have a long string of mediocre films, that the economics tends to work if you have what you call a breakout phenomenon, a breakout film. I may, at this point in time, conclude that the future is going to differ somewhat. It's going to depart from the past. So I may go to someone else and say, give me a subjective probability assessment. What do you think our breakout ratio is going to be in the future? Now, just a word about subjective probabilities. They may be good. They may not be good, depending on the expertise of the person that I'm asking. As a story, when I was about 15 or 16 years old, I remember very distinctly getting in an automobile and riding in the back seat, going to a basketball game with my next-door neighbor. Now, driving the car was my next-door neighbor's father, and sitting next to him was his wife. And all of us, we were driving down the car, and I heard, driving down the street, and I heard this woman, who was a very nice woman, but had a very difficult time dealing with driving. Every time a car would come from the opposite lane, she would go, ooh, ooh. And I thought to myself, well, what's happening here? I mean, I started to get nervous in the back seat, and what was happening was that her subjective probability assessment of being hit by the car coming from the opposite direction was very high. Mine was, you know, maybe 1 in 1,000, maybe 1 in 1,000,000 it's going to occur that some car is going to come over and hit us. Well, hers, I don't know what she was thinking. Maybe she thought it was a 30% chance, or I don't know what she thought it was. But I just know that with every car that came by, she would go, you know, ooh. Now, this woman, my mother still is alive, and this woman is still alive, and now the latter part of her life, she lives pretty much by herself. She's not comfortable with leaving the house, because sometimes we build up subjective probability assessments which are not totally accurate. So if I want to know the probability that AT&T is going to acquire a regional Bell operating company, for example, I may want to ask a knowledgeable Wall Street analyst compared to my aunt. And I may get a better probability assessment subjectively from the Wall Street analyst. Now, I can also count probabilities. I can actually do some mathematical counting. And let me give you an illustration. So I've got experimenting and relative frequency. See? I've got experience or subjective probability assessment. I can also count. Let's solve a little counting problem for you. Let's say the following occurs. Let's say that I am going to have 3 children in my family. I planned this, right? I'm a perfect planner. And I want to know the chances of getting 2 daughters in this family. Okay? And I'm going to make a simplifying assumption here that the probability of getting a male or a female is equal. It's not quite the case, but give me that simplifying assumption. The probability of a male birth and a female birth is equal. So what I do is I count. I can list the possible families that I could get. And since each one is equally likely in my model, I can list them out. I could have 3 males. I could have the first 2 male, second female. I could have male, female, male. I could have male, female, female. I could have female, male, male. I could have female, female, male. I could have female, male, female. And I could have 3 girls. Okay? I've listed all the possibilities. Now, to answer my question, I just have to count. What's the chances of getting 2 females? And this one works. This one works. And this one works. Male, female, 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 male, and female, male, female. So the answer to the question is the probability of having exactly 2 girls in a family of 3, assuming that it's equally likely on each birth to get a male or female, is 3/8. There's 8 possibilities, 3 of them work, so there's a 3/8 or a 37.5% chance of having 2 girls. Now this is my family. I have 2 girls and a boy in my family, so that was the odds of that occurring, of course, before I had any children. Now after events happen, then of course things change. That's what we mean by counting the possibilities. Now finally, I want to talk about mathematical calculation. And we'll deal more with this with our next lecture when we deal with more complicated, more subtle probability assessments. I can calculate mathematically. Now this is kind of calculating mathematically, but just counting. That's all I'm doing here with the male, female, 2/3 girl example. I can actually calculate probabilities, and there are rules for doing this, and we'll discuss some of these more next time. Let's say the following. I want to know the chances of sinking 10 free throws in a row. Okay? Now let's assume that the probability of me making each one is the same. Let's say I'm a 60% free throw shooter, which is not super high, but it's not bad. That the probability of me sinking 1 free throw is 60%. The question is, what are the chances that if somebody comes up, I bet you can't sink 10 in a row. What are the chances that I would sink 10 in a row if I have a 60% chance on each one? Well, it turns out, as we'll see next time, that the probability of 10 in a row is nothing more, assuming these are what we're going to call independent events, and we'll define that more precisely next time, 0.6 to the 10th power, which means multiply 0.6 together 10 times. And the answer, if you do it, is about 0.006. So I won't do it in 100 tries. I'll do it 6 times in 1,000 tries if indeed I fit the probability profile pattern that I've described. Now notice, by the way, that I'm ignoring things such as the hot hand. People talk a lot about the hot hand phenomenon where someone starts to shoot in a streak. That would complicate this model and have to build a better model to deal with that issue. So, to summarize about probability, there are 4 ways that we can derive it. 4 classic ways. Experimenting and counting relative frequency. So I see the number of defects or number of successes, my response rate based on my total mailings. I can do a subjective judgment, and I go to sophisticated people or people whose opinion I value, and I ask them, what do you think the probability is? Or I may combine these to develop my probability estimates. I can count the possibilities if I can list them out, or I can calculate. numerous probabilities mathematically if I make certain assumptions about what's likely to occur and how the events relate to each other. The bottom line on probability is this. The goal of probability is to understand what's likely to happen in future situations, whether it's how many girls I will have in my family, or whether it's the likelihood that I will have positive cash flow from this investment 3 years out. And I make those future assessments within systems I know something about. That's why I have to make probability assessments. I have to be able to come up, get my hands around probability. It's unlikely that we can predict perfectly the future. But using probability, we may be able to describe what is likely to happen.